Our next presentation is entitled Addressing the Limitations of Peanut Resistance Due to Narrow Genetic Diversity. The presenter will be Soraya Bertioli. She's involved at the Center for Applied Genetic Genome Technologies at the University of Georgia.
Share screen. Okay, it's not working. No, just click. No, it's not working again. Let me try that again. Share. Sure.
And just so you know, we've got people involved in the presentation virtually, so that's why we're going through these steps. You're not alone.
So whenever you're forward, if you can click through.
Oh, good morning. Again, very nice to be here, to see everybody again. It's really great pleasure, and thank you very much for the invitation to be here. I love that they put me to talk in the Sustainability Symposium, because I think that's a recognition that the wild species have a space and have a place in the sustainability of the peanut industry. So not only, I would like to show you, if somebody's not convinced yet that the wild species are important, they have been important, they will be important. I hope at the end of this talk you will be convinced. So, just started to say, just great, I love that you ended, right? You ended now talking about your consumer, because here peanut is grown everywhere in the world, and these are the numbers here, the percentages and the productivity. So in the United States and probably in Argentina, we have the highest productivity, highest yields, and in Africa, we have the lowest yields. And who is our consumer in these places? So if you go to Africa, the production is done mostly by hand. There's a little bit of cash crop, but most of it is done by women. And they use peanut for feeding their families, to exchange. They sell a little bit. And also, RUTTF, it's some of these is used for relieving and saving more over million lives a year. So these are very important, but the productivity is very low. We go to Asia, who's producing is varied, is mechanized, and is also by hand. And we want to feed a very large and growing population. When you go to South America, we don't see the consumer here because, South America is not very much consumed. It's mostly grown for export market. We have this big thing in South America that we are being blamed for the destroyed biodiversity. And to some extent, this is true. So we need to find a way to grow more peanuts in a smaller area. And how can we do that? Let's come to the United States, to North America and Europe. So we grow here mostly mechanized agriculture, highly productive, high input, and we export to Europe. We have this love and hate relationship because we need to please the European consumer, European market. And who is the consumer here? Who we're talking about? We're talking about a consumer that is very sophisticated, very demanding. Everything is highly mechanized. And who is this consumer? This is the one, meat, our main consumer here, meat Nadia. So who is she? So she is mostly an urban person, middle class, someone who's educated, who's worried about her health, and she's talking about functional foods. Now, the consumer is changing. We don't only eat peanut in natura, we have peanut. We have some people who really want to take a step forward and that food is their medicine. But, you know, sometimes they make the right decisions, sometimes not. You know, look at her blog, the top functional foods, it's boom chicka pop. I mean, really. And she is also getting peanut and putting into pesticides and carcinogens. I mean, so, and that's a person who has a voice, and we have to listen to her. And what we need to do is we need to change, you know, we need to engage in the conversation, change that perception. She has a voice and she's there talking about, you know, climate change. And agriculture is getting a big hit because agriculture we blame for a lot of the emissions. We know it's not true. If we look at the data, you know, we are responsible for 11% of emissions and such, not talking about the carbon sink as well. But, you know, this is not what the media is saying. And Nadia is looking at these big letters and she's worried about environment and she's blaming agriculture. So that needs to change. The consequence, one of the consequences that a lot of the defensive agrochemicals are being banned. And we see that, I mean, that's happening. Methyl bromide was banned in 1905. Chlorothalonil has been banned in Europe, and chlorothalonil is very important for leaf spots here in the United States. So that affects directly how we produce peanuts in this country. So we have the farmers, you know, struggling, and we have people really saying, well, let's ban pesticides from our food. And on this year, we had a big hit with some insecticides, so that's going to be interesting to see how it pans out. So the tools have been taken away from the grower. And still the farmer, the margins are very small. I mean, the grower still, it's about 25% of the cost of the peanut growing is in defensives. And we saw earlier, it's something like 48% of the carbon emissions. So it's, you know, we need to reduce that. Well, this is how we need to get some super peanuts, some super plants growing. So, of course, I'm here to talk about crop wild relatives, peanut wild relatives. And what are they? We haven't seen any. So I'm going to make a little bit of a parallel here. The peanut is our George Clooney. It's good, it's perfect in every way. But even George Clooney has some long lost cousins in Ireland. It is true, actually. So, you know, he doesn't really want to be associated with this guy, but anyway, you know, what can you do? They're cousins, they're not as good looking, they're not as, you know, doesn't have many qualities, but these are peanuts, our wild peanuts. They're small, they're scraggy. You look at them, you're not interested in eating these things. But, you know, I want to show you how important they have been and they will be for the peanut industry. So there have been a lot of research over the years on how these wild species, they have resistances to all sorts of diseases and pests. There's a lot of research on it. And this is, Tom Stalker made a little review on that, which is very helpful. So the way it is, the reason for that is, you know, we have the wild species are in South America, and this is a distribution, the geographical distribution of the wild species in the coordinates in South America. This is just the Arachis section, by the way. So if we zoom into the region where peanut originated, now we have about these, that's how it looks like. So you can imagine peanuts growing in that region, wild peanuts growing in that region. If you go up north a little bit where, you know, you have this configuration, you have riverbanks, they grow in riverbanks. That's how a lot of them are spread. You have in soggy areas, marshlands. Now you can imagine a wild peanut in a marshland that is flooded a lot of the time. You can imagine this would be interesting for pod rot, maybe for stem rot. So we can put our heads to think that in these different regions, you can have different resistances. If you go to Brazil, some of these areas that are very dry, the Caatingas in the northeast, or the dry Cerrado savannas in Central West, again, they're very dry. So maybe that some of these can be intolerant to heat or to drought or some aspects of drought. Again, we go to the more coastal area. By the way, this is not, we're not planning a beach holiday. This is actually where some of the Arachis Sperm were collected by the beach. So, maybe these would have salinity tolerance. So we look at these things and we see the diversity in terms of morphology. We see diversity in terms of tolerance to diseases and to abiotic stresses. But peanut, it has a completely different story. Peanut, if you look at this little semicircle in the middle, this little area, that's where peanut originated. We're pretty certain of it now because of the genome sequence and a lot of investigation that was done before. So the history of peanut goes hand in hand with the Amerindians, with the native South American people. So these people, about 10,000 years ago, they were eating peanuts already, but they were the little wild species. They had little gardens, they grew plants already, and they would bring seeds from different places and plant them in their little backyards. So we have these two species here. They did not coexist in the same areas. They were brought together by these people, and they are not compatible, but probably a bee, or we blame the bee. We think that that's what she did. So they crossed, and with the knowledge we have now, we know that the progeny was not fertile, but because of spontaneous chromosome duplication, a proto-peanut, something that resembled peanut, well, it didn't resemble peanut, was still very similar to wild, arose. But because of selection, domestication, these people were selecting the best seeds and the best plants, and we have our peanut. And our peanut, as we know today, is lovely, but it is very susceptible to a number of pathogens and diseases. This process took about 10,000 years. And what happened here, if you look at any book that talks about erosion of allelic diversity, we see these little funnels. If you look to the left, to your left, we have the whole genus Arachis with lots of different shapes. What does that mean? We have a lot of diversity, a lot of different alleles that will make them grow in different areas. Then, as we go a little bit further, we have Arachis cardinals, which are the only two species that peanut originates from. So we have a much reduced gene pool. Then once they get together and the genome gets duplicated, the resulting progeny does not cross. We don't have gene cross anymore. So we go reducing much further the gene pool. And we get the peanut that has only a few alleles. So what do? We try and get these alleles back from the wild species. But we cannot do that. It's completely locked because of the difference in genome, in chromosome number. So we have to go back to nature and try and mimic what nature did all those years ago. And we need to find, it's completely locked. We need to find the keys to that. So we go to nature again and see how can we do that. This, by the way, was not thought out by us. This was done many years ago. These are not new ideas. These are just very good ideas. And of course, the first person to some of the first people to do that are in this room. One of them is Charles Simpson. So what can we do? Let's look at nature and see what happened here. So instead of the arboretums, we have to do this nowadays. We have to get somebody to do that here. Instead of the bee, we have a pair of tweezers. We have to go physically and cross the pollen from one plant to another. Instead of a natural hybridization, natural chromosome duplication, we have to do it using chemicals. And we produce induced tetraploids. And then what we do is nowadays we do Marquis's selection, Marquis's breeding, and we get a peanut that is much improved, that doesn't have so many susceptibilities. And it's sort of taking 10,000 years. We hope that it's going to take a lot less. So we have an increased demand for this process to happen. And like any process, we need major ingredients. We need the raw materials, which is the wild species. And again, we cannot stress enough the importance of the germplasm bank at the USDA. We are not able to get, because of the international conventions, seed exchange has been reduced. We are not able to get anything else from South America at this point. We have here about maybe 60-65% of all the species, with all the exceptions, here in the United States. A lot of them in the USDA, some in Texas, and they are being transferred to the USDA with funds from the Peanut Research Foundation. So this is amazing, this is a great achievement. So we really have to look after what we have here because it's irreplaceable. We have expertise and we need to carry on training people. We need to get young people on board because this is the future, this is what we need to do. And not only need to train people, we need to keep the good people we have. Sometimes the university is not able to retain people. We have to make sure that all these good people stay and they pass their knowledge. And we need the tools, and we have the tools. Our tools before were just, we have tweezers and a few more things. Now we have a lot more. Now we have the peanut genome that really guides us to what the regions that we need to select from these wild species. So we're not walking in the dark anymore. We have a lot of light now. And if you're still in doubt if that actually works, so I want to show some examples here because that has been working for many years. And I know that it's a surprise to see some of the cultivars actually have all species. So let's go back to them. So I'm going to talk about Arachis Cardinals. So the Arachis Cardinals is probably, it is certainly the most used, the most useful wild species so far. It comes from Bolivia and came to the United States late 50s. It was collected in 1952. And the first release of a cultivar with Arachis Cardinals was Coam in 1991. So this is the first one, but it was the start of a series of other releases. These are just some examples in Texas. And they were transferred to Rona-type cultivars, again come to Georgia, to the east part of the country, Georgia 19N. Then from another cross, Bailey also has resistance from Arachis Cardinals. And this was a document by David Jordan that says that the total estimate of the value for a decade of Bailey is $127 million. And we're just talking about one cross, one species, one accession, one cultivar. The numbers are much higher than that if you aggregate all the cultivars together. Not only that, but it's not 50 countries, 30 countries. These got spread to different places. It was sent to Phil Moss in India, and it was spread to other countries through APRES and ended up going back to Brazil. Anyway, that's a beautiful story. But over 30 countries have these segments of Arachis Cardinals now. There's a cultivar for the organic market in Brazil called Sempre Verde. There are some cultivars are being released next year, which will have unprecedented levels of late leaf spot. Cardinalsia also is a source of resistance to smut that was found by the Guilherme Seja's group in Argentina. Another species, Arachis dioroi, and that gave rise to several cultivars in East Africa that are resistant to GRD, groundnut rosette virus, which is absolutely devastating. So that's saving a lot of acreage in West Africa, East Africa. Going to Arachis dominensis, which is one of the parents, is actually mother of peanut. Arachis dominensis is being giving some higher yield on the drought. This is in the northeast of Brazil. Moderate early and late leaf spot resistance, also in Brazil. And probably the biggest impact is in Senegal, always in West Africa. Several countries there, what we're seeing is that some of these cultivars that were released in 2016, they have very good yield stability, they have high yield in the drought, they have larger seed. So they are making a real impact in a lot of the countries in East Africa. And the one we have been focusing on, and we really love this species, is Arachis Sperm. We've been working with Arachis Sperm for a few years now, and this was collected by José Vaus in Brazil, in Mato Grosso. The place where he collected it looked a little bit like this. You see this, it's an urban area, and this city grew tremendously. When you know that 25 years later, that's what we found. Even the tree that was planted had been cut down. So this accession is no longer where it was first collected. It is in John Brazovans in South America, and it is here in Griffin. So this is a very, very important accession that we've tested for a number of things, and we created a population that was selected for root nematode. This is Carolina Bagena, a PhD student. These plants are being tested now in Tifton, and they have very, very high levels of resistance to root nematode. And they also have extremely high levels of resistance to rust. These have been tested in Haiti now, and it's better than anything else they've had before. So we see great prospect for this material. We test them in the mid-yield, and not only they're resistant, but they also have very high yield. A lot of the lines have much higher yield than Georgia 6G. So we are hoping to release these materials soon. So just showing a little bit how this happened in time. I showed you before, we had the first wave was Arachis Cardinals. So I'm showing here on the left-hand side, this is the tree, the genetic that we constructed using accessions from all the species of the Arachis section. This was an effort, a joint effort between us, Griffin, and Sean Tallery, Dr. Charles Simpson, Dr. Guilherme Seja from Argentina, and Dr. José Vaus. So we got DNAs from all these places, from all the species of the Arachis section, and we were able to genotype using the AFI chip. And we managed to get the structure of the genus in one place, and that's really very helpful. These gave us a lot of power to understand what happens in each of these clades, and we're being able to direct our crosses now, so we can cover each of these clades. So this little triangle is where Arachis Cardinals is located. And this is the timeline. I'm not sure if you can see. The first cross reported with Arachis Cardinals was in 1967 by Smart. And the first, these are the releases of germplasm in green and cultivars in yellow, and how it was spread around the world. So what I want to show is that it took 27 years between the first reported cross and the first release, first registration of germplasm. So now we have this second wave, which is all the other species, we hope. We have Arachis renescens and ipaensis, and we're having all these triangles and crosses that we have done, we have made. Allotetraphores have been created, and or diploids that are on the way. And our objective is to put a dot in every single one of these clades. And we want to create a bank, which is a core collection that's going to make all this material available to any reader, any researcher who requests it. What happened now is on the top are the releases in the United States, and the bottom releases abroad. And there was a gap of 11 years between the cross and the first release. And what we hope now is that we can shorten these gaps more and more with the genomic information. We're making more and more crosses, introducing it into the peanut crop, and we're making it available. So I think the key here is availability. And as these materials are being transferred and sent elsewhere, this is happening not only in the United States, but in other parts of the world. And our main consumer of our research, our main user, who we cater for, is the peanut industry in the United States. It's the grower, the sheller. The grower is the first one who's getting the direct benefits because this is increasing their production costs. But other places in the world also use these materials, and we have sent materials to other places, and we continue to do so. And we ask, why do we do that? Because we need to strengthen our industry in the United States. And the reason is there's a growing population in the world that needs to be fed, and needs to be fed efficiently using less land. And these women need to feed her child, and these children in Haiti, they need to have food before they go to school. So we have a mission here. We're a rich country, we have a mission to help feed the world while being profitable, while having sustainability in our production here. And this is one of the people we look up to. He says, almost certainly, however, the first essential component of social justice is adequate food for all mankind. Again, we still have this consumer. So we try to feed the world, we're reducing our inputs. So what we want to do, we want to get NADA to rest assured that the risk of getting cancer from eating a peanut is non-existent. We have to assure her that instead of eating bone chicken pop, she may think of other ways to make her health better. So how do we do that? There are many phytocompounds and active compounds in peanut. This was shown before, and I'm ready to show before because peanut, we know that wild peanut has a lot of these bioactive compounds in higher percentages, high concentrations than cultivated peanut. So we can improve cultivated peanut by looking at the wilds and seeing how we can improve it. We have another consumer here who's demanding that also Bob, he wants high oil in our peanuts. So how can we make Bob happy? Now, we know that some wild species do have very high oil content. So there's studies with that already, and this is research that can be done, should be done, and it can help the peanut industry. And now we have also the industry, the manufacturers talking about flavor. Markets for flavor. We need to improve the flavor. Yes, we do. So we know that tomato, which is a small commodity compared to us, there was a remarkable feat that our relative of tomato, I can't even say the name, this Lycopersicum something, increased the flavor. The sweet tomato was transferred to the traditional tomato, and just per year they increased between $5 and $8 million their profits. That's just in a small tomato. So we can do better than that. We can do a lot more than that. We know the wild crop relatives are estimated to contribute genes to cultivated crops worth between $115 and $200 billion per year. So we have a gold mine here. We need to explore it. So summarizing, what I'm saying is that wild peanut relatives, they can contribute to sustainability of the peanut crop. They decrease application of defenses, increasing profit margins, can increase yield, decrease in environmental impact, can increase resiliency in places where they can't have inputs, and that increase food security around the world, and have no compounds, and have no markets, so the sky is the limit. So let's look into it. So I hope I have convinced you that wild species are very important, they have been and they will be. And we are very excited to be part of this journey, and we're very excited to be here again. We're happy to talk, to communicate, to partner, to make this happen. I'd like to thank our lab for an amazing group of people who really make these happen, and our funders and our friends from the peanut community. Thank you.
We've got time for a question if there is one from the audience. Okay, thanks. Thank you.
Thank you, Victor. So for the people who didn't hear from the audience elsewhere, Victor was suggesting to look at amylcellulose, the fiber content, and the shells. That's a great idea, and it's good to pursue that. Thank you, Victor. Thank you.